All right, ladies and gentlemen, welcome back to day 4. We're discussing box plots, outliers, and describing a quantitative distribution more completely now. All right, so there's a third graph that we frequently use to analyze quantitative distributions called a box plot. And a box plot, also known as a box and whiskers plot, is a graph drawn above the number line that denotes the 5-number summary and encloses the visual representation of the interquartile range, the IQR. All right, we are also better able to visualize extreme values and recognize those that are considered outliers through a box plot because they're actually graphed separately from the rest of the data. All right, now first let's discuss how to identify outliers. It's kind of one of the final components to giving a really good description of quantitative distribution. All right, now in addition to serving as a measure of spread, the interquartile range is used as part of a rule for identifying outliers. Although there are other rules for determining outliers, the rule outlined below is often preferred because it is calculated using measures that are resistant to extreme values, such as the interquartile range. All right, this is called the 1.5 times IQR rule for outliers. And we call an observation an outlier if it falls more than 1.5 times the interquartile range above the third quartile or below the first quartile. All right, the data points are considered low outliers if they are less than the first quartile minus 1.5 times IQR, while those that are higher than the third quartile plus 1.5 times IQR are considered high outliers. Now, I want you to take a look at this graphical representation of a box plot. We have our first quartile and our third. Now, if you take a look at the distance from the first to the third, that is your interquartile range. If you go about half again that distance and you add it on to the third quartile, all right, you are looking at the boundary for what's considered regular part of the data set. Anything outside of that is considered an outlier. If you take that same distance and you subtract it from the first quartile over here, anything beyond that is also considered an outlier, but on the lower end of the data. The reason that you are adding onto the third quartile and subtracting from the first, and I just noticed that this seems to have a 2 instead of a 3. You actually want that to say third quartile. When you're moving to the left on a number line, you're going smaller, and anytime you go smaller, you are subtracting. So first quartile minus 1.5 times the interquartile range takes that length that we want to move beyond the first quartile, and it moves it to the left so that we can actually find that lower boundary at the end of our data set. Adding on to the third quartile, anytime you're going to the right, you are increasing your numbers, and to increase, you have to add on, which is why we add 1.5 times the IQR onto the third quartile to find this upper bound. Any points outside of those limits are considered outliers. Any points directly on the limits or within are considered just regular points within the data set. They're not considered too extreme. All right, now let's discuss how to make a box plot itself. All right, so to make a box plot, we want to label and scale a single number line. That means going by 2s or by 5s or by 1s. You want to make sure that you're scaling it properly. And then title your number line. All right, that's the label. Draw a central box from the first to third, first quartile to the third. All right, and then draw a line in the box that marks the median. Draw lines called whiskers that extend from the box out to the smallest and largest observations that are not outliers. All right, note that they will end at numbers that are not outliers, that are actually part of the data set. And if there are any outliers, identify them as points or asterisks at the appropriate place above the number line in line with the ends of the whiskers. All right, so you can see a visual description over here of what I mean by each of those things. All right, so the box plot and 5-number summary for my fall 2017 AP Statistics classes are provided below. All right, using the 5-number summary we calculated yesterday, let's add a box plot representing my fall 2021 AP Statistics classes to our existing graph after we determine if there are any outliers in the data set. We can't actually draw a complete box plot unless we determine whether or not there are outliers. So let's try that outliers formula. For the lower bound, we need, so I'm going to go ahead and write out lower bound. We need the first quartile minus 1.5 times the interquartile range. Now yesterday I calculated the interquartile range as 67 minus 62. Remember our third quartile minus our first, which gave me 5. All right, so I'm going to be using that calculation as we go through this. So my first quartile is 62 minus 1.5 times 5, my interquartile range. All right, so I'm taking 62 minus, 1.5 times 5 would give me 7.5. So 62 minus 1.5 times 5, give me 54.5. Now you can either take 1.5 times 5 and then do your subtraction, or you can just type it all in like I did to get this number. Either way, it's going to work out kind of the same. Now take a look at my minimum. My minimum value is 59. That is within the lower bound. For my outliers, it's not below this. All right? Any number smaller than 54.5 would be an outlier, but we don't have any numbers smaller than 54.5. Our smallest number is actually 59, which is above that lower boundary. So we have no low outliers. Now high outliers would be calculated by taking the third quartile. Ooh, I'm having trouble speaking today. So the third quartile plus 1.5 times the interquartile range. That means that we are looking at 67, which is our third quartile, plus 1.5 times 5. And this time I'm just going to go ahead and type all that into the calculator. So 67 plus 1.5 times 5 gives me 74.5. Now again, take a look at our maximum. Our maximum was 72. We need to have numbers larger than 74.5 to say that there are any outliers on the high end. Our largest number was 72. That's not high enough to be considered an outlier. So based on these two boundaries and our maximum minimum, it looks like we have no outliers, which makes our box plot much easier to do. Now, parallel box plots are when you have two or more box plots using the same exact number line. Notice that my number line is already scaled. I started at 56 over here. I went by 2s. That means that directly in the middle of any of these tick marks is going to be the odd numbers. I have my title, height in inches, so that I know what these numbers actually represent. It's very important to have that title. No title, no usable graph. No matter how pretty it is, unless you know what those numbers represent, it's completely unusable. All right, so please make sure that you actually title your number lines. All right, if you include more than one box plot on the same number line, you also have to identify which data set the box plots belong to. Notice I have fall 2017 here next to the box plot that represents my fall 2017 students' heights. And up here, we're going to have fall 2021. All right, my minimum is 59, so right in the middle there, I'm going to need a little tick mark to show the end of my whisker. First quartile is 62, right, same place where the other one was. My median is at 65, so right in the middle there. If you get one of these a little bit longer than the other, that's okay. It's one of the reasons we use pencil, so we can clean it up. And let's see, 67. So again, a little bit kind of halfway between the 66 and the 68. I'm going to go ahead and draw the outer parts of my box. All right. Connect my first whisker and now my last whisker. The maximum was 72. Right. And as you can see, from my median to my maximum and my median to my minimum, it's almost the same distance. And it's a little bit easier to see that this one is roughly symmetric compared to this one. Right. That's how you make a box plot. Now, our part 3 of how to describe and compare quantitative distributions. So let's kind of talk about this. Now let's put it all together. So when asked to describe a quantitative distribution, statisticians must describe the shape, center, and spread as well as any outliers or departures from the overall distribution. Don't forget to use the shape and presence of outliers in a distribution when deciding which measure of center and spread to use in your description. The median and interquartile range are considered resistant measures of center and spread. In other words, they provide an unbiased measurement in the presence of outliers and skewness. They're not affected by them. The mean and standard deviation should be reserved for distributions of descriptions of symmetric and or uniform distributions without outliers. Now, uniform distributions are distributions where you have about the same proportion of each data point within the distribution. So it's not sloping one way or the other, it's still symmetric, but you have the same amount of points all the way across. Right? Those do happen sometimes. Right? Here's a graphic of different shapes of distributions and also a description of which measure of center and spread you should use in each case. All right, mean goes with standard deviation, median goes with interquartile range. And remember, if the distribution is roughly symmetric, use the mean. For skewed distributions, use the median. Standard deviation describes how far off on average the data points were from the mean, which is why it's used with mean as its measure of center, as its measure of spread. And the interquartile range is always used with the median because you're finding the difference between the median of the lower half and median of the upper half. Those are your first and third quartiles. Right. Now, when asked to compare two or more distributions, a statistician must identify specific similarities and differences between the distributions. Additionally, if one of the distributions requires resistant measures of center and spread, any comparisons made with other distributions should be similarly restricted. Right. So this is just kind of a table comparing mean, median, and mean. I'm going to let you guys go ahead and read that. But we're going to kind of look back at the box plots we completed in example 1, as well as the dot plots and histograms that we completed in the earlier notes. And we're going to provide separate descriptions of each distribution and then compare the distributions to each other. Right, so I'm going to kind of pull this page off so we can take a look at our graphs first, and then we will take a look at the rest of these comparisons. Give me one moment. I just need to locate my earlier graph real quick. There it is. Let's start with the dot plots. What did we notice in our dot plots? All right, so these are from earlier. All right, so I think I said previously that these two distributions seem to have different shapes. All right, for my fall 2021 students, I said this was roughly symmetric. And my fall 2017 distribution seems to be kind of skewed to the right. When you take a look at the histograms that were completed previously, you can definitely see this. All right, this distribution seems to be roughly symmetric, not perfectly, but roughly. While my 2017 students seem to have a right skewed distribution of heights. All right. So you can see kind of the same thing in both. And again, this seems to be kind of single peaked. They both seem to be single peaked. Now, when you're doing separate comparisons, right? So if we just looked at these individually, remember, in a symmetric, roughly symmetric distribution, we use mean and standard deviation. So when I'm describing my 2021 AP Statistics classes, I'm going to go a little bit out of order here. The distribution of heights appears to be single peaked. In other words, unimodal, roughly symmetric, with a mean of 65.03 inches and a standard deviation of 3.38 inches. There were no outliers. All right. Now for my fall 2017 AP Statistics classes. I'm just going to cover this up briefly. I want you to look at the box plot. Notice that there are no asterisks or points at the end of this. That means that there were no outliers for this distribution either. I had calculated that previously. All right, so there were no outliers. However, when you take a look at the histogram, the data is definitely skewed to the right. Now, you can only tell from the histogram and the dot plot that it was single peaked, but you can definitely tell from the box plot that it's skewed to the right. If you take a look at this distance from median to maximum compared to this distance from median to minimum, you can see that the right distance was much longer, meaning the data was stretching much further to the right, and most of the data was clustered in a much smaller space from 58 to 64. All right, so when we describe the fall 2017 AP Statistics classes, in this case, the distribution of heights, I apologize for my handwriting, appears single peaked. Can you see this? Yes, okay. Appears single peaked. Single peaked, right skewed. Now you can say skewed to the right or right skewed. Single peaked, right skewed. I'm going to say single peaked and right skewed with a median of 64 inches an interquartile range, remember that's what IQR stands for, of, let's see, take a look back at our numerical summaries. So 67.5 minus 62 gives us 5.5. Right, so an interquartile range of 5.5 inches and no obvious outliers. And no outliers. All right, so if we were just describing these individually, we would use different measures of center and different measures of spread to describe them because they have different shapes. That's why we have to look at the shape first, which is why we need the graphs. Calculations alone aren't going to do it. You have to have those graphs, you have to have that visual, and you actually need multiple visuals. I would have no way to know that these are single peaked with only a box plot. So I need visuals in order to determine the shape, which then determines which measurements, which calculations I actually need to go forward with. But when you're comparing the distributions, then I have to look at which one is the most restrictive. if I have a skewed distribution, then I can only really compare the median and the interquartile range. I can't really compare this mean and standard deviation I'm using down here. So if I'm comparing them, I'm literally writing down sentences explaining what's similar and what's different. Right, so the distribution of height so the distribution of heights in my fall 2017 versus 2021 classes are right skewed and roughly symmetric respectively. Respectively is a phrase that means in the order that I wrote it in. So because I referred to my fall 2017 class before 2021, it means that fall 2017 heights are right skewed while 2021 heights are roughly symmetric. Very useful word to know. Right? So respectively. They have different medians, or let's not just say different. Let's actually do full comparison. The median of my 2017 student heights is lower I'm having a rough time writing tonight. Sorry about that. Is lower than in 2021. So in 2017, it was 64 inches, 64 inches versus 65 inches. The interquartile ranges were similar, (5 inches versus in 2021 versus 5.5 inches in 2017. There were no outliers. In either data set. So I'm going to kind of hold the paper here for just a moment. Please pause if you need to write any of this down. Right, so notice that when I was doing comparisons, I provided direct numerical support for my comparisons. And I compared the shapes, centers, spreads, and if there are any outliers. And I stated whether they were close to being the same, if they were different, I was kind of literally doing a compare and contrast. All right, now, during class tomorrow, I'd like for you to calculate whether your distributions contain outliers, and then graph a box plot to represent each distribution separately. All right, finally, describe the distributions individually and check with your group members. All right, I will see you in class.